Hello and welcome to this revision session for AQA A-Level Physics Paper 2, where we're going to do some practice questions on the topics of this particular paper. So in today's revision session we're going to look at how to answer examination questions on A-Level Physics Paper 2. So if we've been successful and we've learned in this revision session, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics and understand what topics you need to improve upon for A-Level Physics. So let's start off with the topic of gravitational fields. So the first question says, explain what is meant by the gravitational field strength at a point. Then figure 18.16 shows the dwarf planet Pluto and its moon Charon. These can be considered to be a double planetary system orbiting each other about their joint centres of mass. Firstly, calculate the gravitational pull on Charon due to Pluto. Then use your result to the previous question to calculate Charon's orbital period, and then explain why Pluto's orbital period must be the same as Charon's. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question you've got to learn the definitions of all the key properties of different fields. So the field strength is the force per unit property of the field. So for a gravitational field strength it is the force per unit mass at that point in the field. In the next question we're asking for the gravitational pull, which is another phrase for the gravitational force. So to work that out we've got to use Newton's law of gravitation. F equals big G m1 m2 over r squared. Pop in all the values which are given to you from the question, and the answer is 3.3 times 10 to the 18 newtons. You can then use this to determine the orbital period, because we can link it into the idea that this force is also the centripetal force. So we can therefore work it through and get T equal to be 2 pi times by the square root of mr over F. We can then work it through, pop in all the values, and we get 5.60 times 10 to the 5 seconds. Now it's important why Pluto's orbital period must be the same as Charon's, because otherwise it's a key idea in orbits. If they didn't have the same orbital period they would lose stability in their orbits. So the next question says, a space vehicle has a mass of 16,800 kilograms and is in orbit 900 kilometers above the surface of the Earth. Show that the orbital speed of the vehicle is approximately 7,400 meters per second. Then, the space vehicle moves from the orbit 900 kilometers above the Earth's surface to an orbit 400 kilometers above the Earth's surface, where the orbital speed is 7,700 meters per second. Calculate the total change that occurs in the energy of the space vehicle. Assume that the vehicle remains outside the atmosphere after the change of orbit. Use the value of 7,400 for the speed in the initial orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we can say that the gravitational force is equal to the centripetal force in this situation because it's acting perpendicular to motion and it's causing that circular motion. So we can say gmm over r squared equals mv squared over r. We can then rearrange it to work out what the orbital speed is, because v is going to equal square root gm over r. Pop in all the values. Now again remember r is the distance from the center of mass to the object. So you've got to add in the radius of the Earth to the actual distance above the surface of the Earth, making sure we take our kilometers and turn them into meters. We then pop in our values and we get 7,396 meters per second. Now in the next one it's important to know that the potential energy is equal to gmm over r. We can't use mgh because g, small g, changes in the course of the orbit. We also have the kinetic energy is a half mv squared, so we can therefore work out what the change in the potential energy would be by doing gmm over the difference in r between the different places. And again remember we're taking our value of r from the center of mass of the Earth, not the surface of the Earth, and we can then work out what our change in potential is. We can therefore work out what our change in kinetic is by doing a half mv squared and working out the difference in the velocities in each instance. And you've got your potential energy, which is a negative. You've got your kinetic energy, which is a positive. Remember, in orbits we always consider potential energy to be a negative. We then add the two together and therefore we get 2.99 times 10 to the 10. The next topic we're going to look at is electrical fields. So this question says an alpha particle emitted in the radioactive decay of radium has a kinetic energy of 8 times 10 to the minus 13 joules. Calculate the potential difference that an alpha particle initially at rest would have to be accelerated through this to gain this energy. Calculate the speed of the alpha particle at this kinetic energy. Figure 23.20 shows the path of an alpha particle of this energy as it approaches the gold nucleus head on. State the speed of the alpha particle at its point of closest approach to the gold nucleus. Write down the kinetic energy of the alpha particle at this point. Write down the potential energy of the alpha particle at this point. Use your answer to the previous question to show how the alpha particle will reach a distance of 4.5 times 10 to the minus 14 meters from the center of the gold nucleus, and then suggest and explain what this information tells us about the gold nucleus. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, what's the potential difference? Well, we know that work done is equal to the potential difference times by the charge. We know that the work done in this instance is going to be the kinetic energy as it's going from rest to having that particular speed, so it's gaining that kinetic energy. And we know what the charge of our alpha particle is. It's 2 times by 1.6 times 10 to the minus 19. So we can work it through to be V to be 2.5 times 10 to the 6 volts. In this next one, what's the speed? Well, we know our kinetic energy is going to be equal to 8 times 10 to the minus 13. We know E equals a half mv squared. Therefore, we can work out the mass of the alpha particle by doing the 2 protons and the 2 neutrons masses all added together. We can then work out what V is, and it is 1.6 times 10 to the 7 meters per second. Now, what's the speed of the alpha particle at the point of closest approach? Well, at instantaneous point of closest approach, it instantaneously stops and then retreats. So it's going to be 0 at that point. So if it has 0 speed, it'll have 0 kinetic energy. So therefore, all of its energy will be in its potential store. We know the total energy is 8 times 10 to the minus 13. So therefore, that must be the potential energy. Now, we can then use this to work out our value of R, because we know that the potential energy is equal to Q1, Q2 over 4 pi epsilon 0 R. So therefore, we can rearrange it, make R the subject. We know what the charge of an alpha particle is. It's 2 times by 1.6 times 10 to the minus 19. We know what the charge of the gold nucleus is going to be. It's going to be 79 times by 1.6 times 10 to the minus 19, because you've got 79 nucleons, or protons I should say, sorry, in the gold nucleus. And then you can work it all through, and we get 4.5 times 10 to the minus 14 meters. Now, it's important to know what this tells us about the gold nucleus, that in theory, the maximum possible nucleus is going to be 4.5 times 10 to the minus 14 meters, because that's as close as the alpha particle can get. In reality, it'll probably be slightly smaller than that though. The next question says, point charge A of 2 nanocoulombs and B of minus 3 nanocoulombs are 200 millimeters apart in a vacuum, as shown in the figure. The point P is 120 millimeters from A and 160 millimeters from B. Firstly, calculate the component of the electrical field strength at P in the distance AP. Calculate the component of electrical field at P in the direction PB. Calculate the magnitude and the direction of the resultant field at P. Explain why there's a point X on the line AB at which the electrical potential is 0, and calculate the distance of the point X from A. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to use the electrical field equation, which is the electrical field strength is going to be equal to Q over 4 pi epsilon 0 R squared, because it's a point charge. We can then pop in all the values and work it through. Now, the distance between A and P is a straight line of 120 millimeters, so that's 0.12 meters. Pop in all the values and we get 1,200 volts per meter. We then do the same for PB. Now again, PB is a straight line distance, which we know to be 0.16 meters, so pop that in and it's 1050 volts per meter. So what's the magnitude and direction of the resultant field? So firstly, how can you work out the magnitude? Well, we've got to use Pythagoras because it is a right angle triangle. Always look for your right angle triangles when you're working out vector sums. So it's the square root of 1250 squared plus 1050 squared, so it's about 1630 volts per meter. We can then, if we look at the right angle triangle, find the direction by doing a bit of trigonometry. So we can use SOHCAHTOA, TOA opposite over adjacent, so you can use that to get your angle to be 50 degrees. Now, why is there a point where the electrical potential is zero? Well, you can see here it's all about the charges. So the potential due to A, because it's a positively charged object, is going to be positive. The potential at B is going to be negative because it's a negative charge. So there's going to be some point in the distance between the two of them where the positive and the negative will completely cancel through, so the sum will equal zero. Now on the last one, what's the distance? Again, you've got to use a bit of trigonometry. You've got to then work it all through. So you can work it all through there. You can see the trigonometry is going in there. So we're looking at our potentials. So we're working it through because at that point they're going to equal 0. So you can work out what x is going to be by looking at this idea of trig. Okay, remember it's 0.2 meters from A to B. So one is going to be x and one's going to be 0.20 minus x because it's just thinking of that relationship. So therefore x is going to equal to be 0.080 meters. Let's now have a look at the topic of capacitance. So a 250 microfarad capacitor is fully charged from 6-volt battery and then discharged through a 1 kilo ohm resistor. Calculate the time it takes for the charge on the capacitor to fall to 37% of its original value. Then calculate the percentage of the total charge remaining on the capacitor after 0.7 seconds. The charging voltage is increased to 12 volts. Explain the effect this has on the total charge stored in the capacitor, the capacitance of the capacitor, and the time taken to fully charge the capacitor. Then a fully charged 320 microfarad capacitor is discharged through a 1.6 kilo ohm resistor. Calculate the time taken for its voltage to drop to half of its value when it's fully charged. So pause the video now, then unpause the video and you'll want to go through your answer. Right, in this first one, you've got to remember that the time taken for the charge on a discharged capacitor fall to 37% of original value is a time constant. And we know the time constant is RC. So you've got R, you've got C. Now remember, you turn microfarads into farads, you turn kilo ohms into ohms. So therefore you get 0.25 seconds. In this next one, we can use the discharge equation of Q equals Q0 e to the minus T over RC. We can then work out what our value is going to be in terms of Q0, because that will tell you the percentage of the total charge remaining, because Q0 is 100%. So therefore it's going to be 0.06 Q0. So if you work it through, it's 6% of its initial charge left. Now this next one, you've got to think logically how it all works. So the total charge stored will double because we know V for a capacitor is proportional to Q. Now the capacitance is always a fixed property of a capacitor unless its dimensions change. So the time taken to charge doesn't change because if you think about it, T is going to be only dependent on R and C, the time constant equation. So they don't change in this instance, so you can see the effect it will have. Now in this next one, how do you work out the time taken to drop to half of its value? So you've got to remember that the time taken for a capacitor to discharge by half is 0.69 or log 2 RC. So you pop in all the values. Remember, we turn kilo ohms into ohms, microfarads into farads, and we get 0.35 seconds. The next question says, a 450 nanofarad capacitor has a charge of 3.24 microcoulombs. Calculate the energy stored by the capacitor. A capacitor is being charged. By what factor does the energy stored by the capacitor change as the potential difference increases from 5 volts to 10 volts? Then a capacitor is connected to a power supply in a circuit and is fully charged. It is then discharged through a resistor. A potential difference of 4.44 volts is measured across the capacitor by a voltmeter after one time constant. What is the voltage of the power supply? Then the capacitor in the previous question has a capacitance of 15 microfarads and a resistance of 650 ohms. How much energy is lost by the capacitor 8 milliseconds after it began discharging? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to just look at what equation can we use for energy stored. We've got capacitance, we've got charge. So we can use our equation E equals Q squared over C, pop in all the values, check your prefixes, and we get 1.2 times 10 to the minus 5 joules. In this next one, we can see from the equation we've got capacitance is a fixed value, but V is changing. So we know E is equal to a half CV squared. That's an equation for the energy stored by a capacitor. So because C is constant, we can see that the energy stored is proportional to V squared. So V increases by a factor of 2, 5 to 10, well then energy will increase by a factor of 4. In this next one, after one time constant, we know V equals V0 e to the power minus 1, because it'd be RC over RC on that exponential power. So when we work it all through, we get our answer to be 12.1 volts. Now in the next question, we can again say V equals V0 e to the minus t over RC. Pop in all the values. Again, we've got all these numbers from the question. Remember, milliseconds turn into seconds, microfarads turn into farads, and then you can work it through to be 5.312 volts. So that's what the potential difference of the voltage left on the capacitor will be. We can then work out our energy by doing E equals a half CV squared. Now, so you do a half times by 15 times 10 to the minus 6 times by this 5.312 squared. So we get our answer out to be 2.1 times 10 to the minus 4 joules. The next question says, state what is meant by a capacitance of 37 millifarads. Then a capacitor is made up of two metal plates which are separated in air by a distance d. A cell of negligible internal resistance is connected across the capacitor as shown. Switch S is closed and the capacitor becomes fully charged. When S is still closed, the plate separation is reduced to d over 2. State and explain what happens to the magnitude of charge stored by the capacitor. Explain how the charge is conserved when the plate separation is reduced. S is now open, so the plate separation is increased to D. State and explain how the energy stored in the capacitor changes during this process. Then explain how energy is conserved when the plate separation is increased as described previously. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to learn what a farad is. So a farad is the amount of charge stored per volt, so it's 37 millicoulombs stored per volt. In this next question, think of what the parallel plate capacitor equation is. C equals epsilon 0 epsilon r A divided by D. So in this instance, the capacitance doubles and the voltage stays the same. We can know that from because it's connected to the same battery as shown. So therefore Q equals CV, so Q will double. Now, how can charge be conserved when the plate separation is reduced? Well, if our charge is doubling, we can't lose electrons, we can't gain electrons. So therefore, what can we say? Well, we can say that an equal number of electrons is removed from the positive plate as is deposited onto the negative plate. In the next question, now because S is now open, there's a break in the circuit, so charge can't flow, so therefore charge has to stay the same. So therefore, what can we say? Q is staying the same as the capacitor is isolated, charge can flow. So therefore, capacitance halves, and we know E equals a half Q squared over C, so therefore our energy will double because C is now halved. Now, how can energy get conserved in this instance? Because the gain in stored energy is provided by pulling the plates apart and putting work into the system. The next questions are all about magnetic fields. So the first question says, a search coil is made up of 5,000 turns of radius 6.5 millimeters. It is positioned in a magnetic field of known flux density 550 milliteslas. Determine the average EMF induced between the contacts to the coil if it's removed from the magnetic field in 0.25 seconds. Then the strongest permanent magnets are made from an alloy of the metal neodymium pellets. Takes 2 seconds to fall through a 30 centimeter long copper tube, whereas an identical but unmagnetized neodymium pellet takes less than 3 seconds. Explain why. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we need to work out EMF. Now, EMF is equal to the change in flux linkage divided by the change in time. Now, flux linkage is N times by phi. So how can you work this through? Well, we know that the area of the coil, because it's a circular coil, is pi r squared. Now, remember, turn our millimeters into meters. We've then got our area to be 1.3 times 10 to the minus 4 meters squared. We then know that we can work out what the change in flux linkage is by doing BAN. So what is that going to be? So it's 5,000, okay, which is N, times by A, which is 1.3 times 10 to the minus 4, times by N, which is going to be 550 times 10 to the minus 3. So that's B. Remember, milliteslas turn into teslas, divided by the time, 0.25 seconds, and we get minus 1.5 volts. Now, this next one is all about the idea of Lenz's law, which is a very important principle to consider in any situation when you've got induction. So at any point, as the magnetized neodymium pellet goes through the copper tube, that portion of the tube will cut the field lines of the magnet, causing current to be induced in the copper due to Faraday's law. Now, because these induced currents create magnetic fields that exert a force on the magnet, it opposes its fall via Lenz's law, because it's got to be produced in the opposite direction to the change that caused it. So therefore it will oppose the falling of the magnet, so therefore fall much more slowly than an unmagnetized neodymium pellet. The next question says, a wire is moved upwards through a magnetic field of flux density 500 milliteslas. The length of the wire that cuts through the magnetic field is 5 centimeters, and it moves through a distance of 2 centimeters in 0.50 seconds within the field. Firstly, determine the area of the magnetic field that the wire cuts through, the amount of flux that is cut by the wire, the size of the EMF induced in the wire, the current that flows in the wire if the combined resistance of the wire and the ammeter is 0.45 ohms. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how do you work out the area? So you've been told here that it's going to be an object with a length of wire which is 5 centimeters and a distance of 2 centimeters. So you convert those into meters and you get 1 times 10 to the minus 3 meters squared. The amount of flux, well, flux is equal to BA, so you've got B, which you know to be 500 times 10 to the minus 3, or 0.5, multiply that by the area you just worked out, and we get 5 times 10 to the minus 4 Webers. Then EMF induced is equal to the change in flux linkage divided by the time. Now the change in flux linkage in this case is going to be the same as the flux because it has one loop, so BAN is going to be BA times by 1. We divide it by the time, which is 0.5 seconds, to get 1 times 10 to the minus 3 volts. And in this last one, remember, it is still current flowing, so you can still use your normal electricity equations. So I will equal V over R. You've got V because you just worked it out in the previous question. You've got R from the information given, so it's 2.2 times 10 to the minus 3 amps. The next question says, electrical power is transmitted through cables of total resistance 1.8 ohms, operated with an alternating current at a root mean square voltage of 11 kilovolts. The power supplied to the input of the cables is 960 kilowatts. Firstly, calculate the peak value of the current in the cables, calculate the percentage of the input power that's available at the output end of the cables, and when public electricity supplies were first introduced, many of the power stations generated direct current. This meant that the premises that were a large distance from the power station could not be supplied economically with electricity. Discuss this by reference to the physical principles involved, stating why AC is now preferred for distributing electrical power. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to remember that with alternating, we know P equals I RMS times by V RMS. So I RMS is P over V RMS. We've got P, it's 960 times by 10 to the 3. We've got R, which is 11 times by 10 to the 3. So you get I RMS is 87.3 amps. Now you can turn that into peak by doing I RMS times by square root 2, because that's just an equation you've got to remember. So you get 123 amps. Now you can work out power loss from electrical cables by using the equation I RMS squared, because it's an alternating, times by resistance. So it's 87.3, which we worked out previously, squared times by 1.8, which is the resistance. The power lost is 13.7 times 10 to the 3 watts. So therefore, the power available at the output is the starting value, 960, minus 14 kilowatts. So therefore, it's 946 kilowatts. So to work out the percentage of the power available, it's the power at the end divided by the input times by 100, 98.5%. Now in this next one, you've got to understand why alternating current is used in the national grid. So power is lost from cables as the electrical power goes through them. The longer the cables, the greater the resistance. Now power is lost from the cables with the equation I RMS squared times by R. So this tells us less power is wasted if a higher voltage is used, because if you've got a higher voltage, then the current required is less for the same power, because in this case P equals IV. So if V goes up, I can go down for the same value of power. Now this means that you can have to transform the current and the potential difference. So this can only work via electromagnetic induction, which is requires a change in flux linkage. So therefore you need an alternating current to produce this change in flux linkage, because transformers cannot be operated by steady direct current. The next question says a transformer is used to step down 230 volts to mains to 12 volts. When a 12 volt 48 watt lamp is connected to the transformer's secondary coil, the lamp lights normally. The transformer has 1150 turns on its primary coil. Calculate the number of turns on the secondary coil. When the lamp is on, the primary current in the transformer is 0.22 amps. Calculate the current in the secondary coil. Calculate the efficiency of the transformer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know what the transformer equation is, and that is NS over MP equals VS over VP. Pop in all the values, you get 60 turns, and that makes sense because in the secondary is a much lower voltage, so therefore there's much less turns. In the next one, we know that power is equal to I secondary times by V secondary, so therefore I secondary is equal to P over V, so therefore it's 48 over 12 and it's 4 amps. And then in terms of efficiency, it is the power of the secondary, the output, divided by the power of the input, the primary. So it's ISVS over IPVP. Pop in all the values, work it through, you get 0.95, which is 95%. Let's now have a look at some thermal physics. So in the first question, an electrical kettle contains 4.25 times 10 to the minus 4 meters cubed of water. The temperature of the water is 22 degrees Celsius. The kettle is switched on. The water takes 85 seconds to reach a temperature of 100 degrees Celsius. Show that the power of the kettle is about 1600 watts and the water boils at 100 degrees Celsius. Calculate the time now taken for 75% of the water to boil away. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can work out the mass because we've got the density, we've got the volume. So we get 0.424 kilograms. We know that the energy change in this case is going to be linked into the change in temperature because we are changing temperature here. So it's MC change in temperature. Pop in all the values and we get 1.386 times 10 to the 5 joules. We know power is energy over time, so you can work it all through to be 1631 watts. In this next one, we're now looking at a change of state. So we know that E equals ml. So therefore we can work this through. Now m is the change in mass, the mass that changes state. So you've got to work out how much of the water is boiling away. So 75% of that mass. Then you'd multiply it by the latent heat capacity and you get 7.19 times 10 to the 5 joules. Time is equal to the change in energy over the power. It's the same equation as before, just rearranged. So you get 441 seconds. The next question says, a truck is to cross the Sahara Desert. The journey begins just before dawn when the temperature is 3 degrees Celsius. The volume of air held in each tyre is 1.50 meters cubed and the pressure in the tyres is 3.42 times 10 to 5 pascals. Explain how the air molecules in the tyre exert a pressure on the tyre walls. Calculate the number of moles of air in the tyre. By midday, the temperature has risen to 42 degrees Celsius. Calculate the pressure in the tyre at this new temperature. You may assume no air escapes and the volume of the tyre is unchanged, and then calculate the increase in the average kinetic energy of an air molecule due to this temperature rise. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've got to understand how you can exert a pressure. So the molecules will hit the wall. Each impact causes a small force due to the fact that there's a change in momentum and impulse on the wall. And because the molecules are in a random motion, many impacts will smear the force over the whole wall. In this next one, we have P, we have V, we have R, we have T, so we can use our PV equals nRT equation. Remember, T is in Kelvin, so you've got to change the Celsius into Kelvin, so it's 224 moles. Again, you can do the same one now, but again, P, V, R, so you got V, you got N, you got R, you got T. Because none of the air has escaped, has the same number of moles as before. T has now changed. Remember, we changed into Kelvin, so it's 315. So you get 3.91 times 10 to the 5 pascals. And you can work out the kinetic energy of one air molecule with our equation E equals 3 over 2 kT. So what you can do is say 3 over 2 times by K, the Boltzmann constant, times by the change in the temperature, and then that is the change in the energy, so it's 8.01 times 10 to the minus 22 joules. The next question says, explain what is meant by Brownian motion and how it provides evidence for the existence of molecules. The density of air at room temperature and pressure is 1.21 kilograms per meter cubed. Calculate the average speed of air molecules at this temperature. Then state and explain the effect on the average speed of air molecules of raising the temperature of the air and of going to a higher altitude but keeping the temperature constant. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what is Brownian motion? It's random zigzag motion of larger particles like smoke or pollen or dust, and the air molecules will collide with these particles. Each collision gives the larger particle an impulse in a different direction, so it shows a zigzag motion. In the next one, we know what our equation is. It is the value is going to be equal to a third p times by v times by c squared. So you can work out what c squared is by doing 3 times by 1.03 times 10 to the 5 over 1.21. So you get 2.55 times 10 to the 5, square root that, 505 meters per second. Now, you know that the kinetic energy is 3 over 2 kT. So if you raise t, well, therefore the kinetic energy will go up, and therefore the speed will increase because temperature is a measure of the average kinetic energy. Now, when we go to a higher altitude, remember kinetic energy is 3 over 2 kT. T is not changed, k is a constant, so therefore the speed will be unchanged. The next question says, the fuel used in a camping stove is butane, which is stored in the canister as shown. Some of the butane in the canister is in a liquid state and some is in a gas. When the stove uses the butane gas, some of the liquid butane evaporates. Explain why the temperature of the canister decreases when the stove is used. The pressure inside the canister is 220 kilopascals and the temperature of the gas is 21 degrees Celsius. The canister is in the shape of a cylinder of length 0.23 meters and radius 0.11 meters. Calculate the number of molecules of butane gas in the canister. Assume the volume of the liquid butane inside the canister is negligible, and then calculate the RMS speed of the molecules of butane gas. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first one, what do we know? So there's an increase in the potential energy of the molecules leaving the liquid, so therefore we can say that heat must be supplied to convert the liquid into a gas, and only the faster molecules have enough energy to escape. So we can say in theory that the work is being done by the gas because the gas is expanding outwards. That's the theory of thermodynamics. So that tells us if the energy is leaving the liquid, well, the internal energy of the liquid left behind decreases. So the average kinetic energy of the molecules remaining decreases. So therefore, if the average energy of the molecules is decreasing, or the temperature is decreasing because the kinetic energy is linked into the temperature of the liquid, so therefore it will cool down. In the next question, we know that PV equals big NKT, and we need to work out N, the number of particles. But how do we work out V? Well, we can say V is equal to the idea of a cylinder, so it's pi r squared times by the height, L. So you pop in all the values, we get our volume to be 8.74 times 10 to the minus 3. We then use PV equals NKT. T is in Kelvin, so it's 294 Kelvin. Work it all through, and N is 4.74 times 10 to the 23 molecules. In the next one, we know a half mc squared equals 3 over 2 kT. We know m from the previous question, so we know that m can be 9.6 times 10 to the minus 26 kilograms. We then know what k is. It's a constant. We know t. It's 294, so we can work out what c squared is going to be. And then you root that to get RMS speed, so it's 356 meters per second. The next question says, air is used to inflate a balloon. The inflated balloon has a volume of 1.77 times 10 to the minus 3 meters cubed and contains 5.15 times 10 to the 22 air molecules. The air inside the balloon exerts a pressure of 1.15 times 10 to the 5 pascals. Calculate the average kinetic energy of the air molecules. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one we know PV equals big NKT, where big N is the number of the air molecules. So we can work out T from this particular equation. Again, so we can work it through to be 286 Kelvin by popping in all the values that we know from the question as given to us. We then know a half mc squared equals 3 over 2 kT. We've got T, we've got K, because it's a constant, we know it's 3 over 2, so we can work out what a half mc squared is, which is going to be the kinetic energy. So you pop in all the values, and it's 5.93 times 10 to the minus 21 joules. Let's have a look at the nuclear physics questions. So cesium is a radioactive isotope produced during the fission of uranium. State what is meant by fission. Then cesium decays by emitting beta radiation. Complete the nuclear equation for the decay of cesium. Then explain why the emission of an antineutrino in the decay leads to a range of energies for the beta minus particles. Then cesium is a major source of radiation from radioactive waste. A nuclear fission reactor produces about 24 kilograms of cesium each year. A website states that 24 kilograms of cesium has the same activity as 2,000 kilograms of radium. Assess whether this statement is correct, and then cesium may enter plants grown in a contaminated area. The radiation from 100 grams of plant material grown in a contaminated area can have a count rate as high as 500 becquerels. A count rate of 150 per minute is considered safe. Determine the time taken for a count rate from 25 grams of plant material grown in a contaminated area to fall to a safe level. So pause the video now, then unpause the video when you want to go through your answer. Right, firstly, fission is when a massive nucleus splits into two or more smaller nuclei or fragments, and you'll also get some neutrons and gamma radiation as well. Now in this next one, we know that beta minus is going to be 0, minus 1. The numbers at the top and the bottom have to be conserved, so therefore barium is 13756. Now you need, when you have an antineutrino in the decay, to conserve lepton number. Well, it will conserve momentum because the nucleus will also recoil. So this will lead to energy being released and shared randomly between the beta minus particle and the neutrino. So therefore, instead of just being between two particles, it's now between three particles in decay, leading to a variety of speeds. In this next one, we can work out what the number of particles is going to be in cesium by doing 24 over 136.9 times by 1.66 times 10 to the minus 27, the mass of 1 U. So you work it through and you get the number of particles there to be 1.06 times 10 to the 26. We know that the decay constant is equal to log 2 over the half-life, so you can work it through in seconds. Remember, convert now years into seconds, so we get 7.29 times 10 to the minus 10 seconds to the minus 1. We know that then activity is equal to minus decay constant times by n, so multiply those two numbers together to get minus 7.73 times 10 to 16 becquerels. That value, 7.7, is not equal to 7.3 times 10 to 16, the value given previously in the question, as you can see here, the activity of radium. So in the comparison, the statement is incorrect. Now in this next one, we know that A0, when it has 25 grams instead of 100 grams, well, it's just going to quarter. So therefore, instead of 500 becquerels as your count rate, it's 125. So if we then do it per second instead of per minute, it's 2.5 becquerels. When we're working it through, because instead of 150 count per minute is equal, when you see on here, to therefore be 2.5 per second. So therefore we can say, well, we say A equals A0 e to the minus lambda t. Pop in all the values. You don't have t, you do have A to be 2.5, you have A0 to be 125. Pop it all through, make t the subject, and you get 5.37 times 10 to the 9 seconds. The next question says, radon is a radioactive gas and emits alpha particles. Explain what is meant by the activity of a radioactive source and give its unit. The half-life of radon is 3.3 times 10 to 5 seconds. Determine the time it takes for a sample of radon to decay to 20% of its initial activity, and discuss the extent to which alpha particles are a risk to the human body. So pause the video now, then unpause the video when you want to go through your answer. Right, so activity is the rate of decay or the number of disintegrations or decays every single second, and it's measured in becquerels. In this next one, we know that decay constant is log 2 over the half-life, so we get it to be 2.1 times 10 to the minus 6 per second. We can then say A equals A0 e to the minus lambda t. We can then work that through to make t to be the subject. We get 7.7 times 10 to the 5 seconds, which is 8.9 days. Now, alpha particles can be a risk because they're safe outside the body because they're stopped by skin, but they are dangerous if they're swallowed or inhaled, and they're highly ionizing, so it can damage DNA, kill cells, cause cancer, and cause mutations in humans. The next question says, in the core of a main sequence star, nuclear fusion is converting hydrogen into helium. Explain the conditions required to bring about and maintain fusion in a main sequence star. A helium nucleus is a particularly stable nucleus consisting of 2 protons and 2 neutrons. Calculate the binding energy per nucleon in joules of a helium nucleus. And then the binding energy per nucleon of helium is relatively large. Explain why this makes the helium nucleus particularly stable. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that in the main sequence star, you must have a very high temperature in the core, because this gives the protons in there, the nuclei, enough kinetic energy to overcome their electrostatic repulsion, because they're all the same charge, positive. And then also, you need to have a very high density to give a high collision rate to get this fusion process going to balance out the gravitational attraction of the star. Now in this next one, how do you work out binding energy? Well, firstly you work out your mass difference, you do your products before, and then your products afterwards, which is going to be the nucleus. So you can do the nucleus, which is 3727.6 minus 2 protons and 2 neutrons, so you get 28.1 MeV over c squared. That's the mass difference. You can then turn that into energy by just removing the c squared, so it's 28.1 MeV. So you can turn that into joules by multiplying by 10 to the 6 to get out of mega, then multiply by 1.6 times 10 to the minus 19 to get 4.496 times 10 to the minus 12 joules, divided by the number of nucleons, and you get 1.124 times 10 to the minus 12 joules. Now, the binding energy per nucleon is the energy needed to remove one nucleon from the nucleus. So if you've got a large binding energy per nucleon, you need a lot of energy to remove one nucleon from the nucleus, so therefore it will be stable, and its decay products will have a lower binding energy per nucleon, because this decay products will be less stable. The next question says, a nucleus of polonium-210 decays to lead-206 by emitting an alpha particle. Show that the energy released in the decay is about 9 times 10 to the minus 13 joules. 98% of the energy from the decay is released as kinetic energy of the alpha particle. Calculate the velocity of the alpha particle immediately after the decay. Then explain why not all of the energy from the decay is released as kinetic energy of the alpha particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that what's the mass difference. So work out the mass before, which is going to be the polonium. Okay, then subtract the lead and the alpha particle from that, and we get a difference of 9.63 times 10 to the minus 30 kilograms. We can turn that into energy by doing E equals mc squared. So multiply that by 3 times 10 to the 8 squared, and we get 8.67 times 10 to the minus 1 joules. That's the energy. So therefore 98% of that, so multiply that by 0.98, equals the kinetic energy, a half mv squared. We know the mass of the value of the alpha particle. You can work it through. It's the mass of 2 protons plus 2 neutrons. Work it through, get v to be the subject, and v equals 1.60 times 10 to the 7 meters per second. Now, you'll never have all the energy released as kinetic energy alpha particle, because in any decay process, momentum must be conserved. So if the alpha particle has a momentum, well, so must the nucleus of the actual decay substance as well. So that must have a momentum in the opposite direction to conserve it. So it must recoil, so it will take some of the energy as well as the alpha particle. The next question says, describe how the fission of nuclei is induced and controlled in a nuclear reactor. Show how the fission leads to the release of large amounts of energy, and the energy released from the fusion of 1 kilogram of hydrogen is more than 7 times the energy released by the fission of 1 kilogram of uranium. Compare the practicalities of using nuclear fusion of hydrogen with the nuclear fission of uranium to meet our energy needs. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what do we do? Well, what's happening in fission? So fission is the absorption of a neutron by uranium-235. It becomes the more unstable uranium-236. The uranium-236 undergoes fission, resulting in smaller nuclei being produced with some fast neutrons. The moderator in the process will slow the neutrons down to be absorbed by other uranium-235 nuclei. The process repeats again and again to form a chain reaction, and the rate of chain reaction is controlled or raised by raising or lowering the control rods, which will absorb excess neutrons produced in the decay process. This will allow 1 neutron per fission to cause further fission. So when you're working out your energy per fission event, you work out the mass of the uranium-236, and then you can find the total mass of the fission products, add them all through. Remember, there are going to be 3 neutrons produced, so you get 235.86658 U. Find the difference, 0.18604 U. Multiply that by 1.661 times 10 to the minus 27 to get that into kilograms. Then work out the energy equivalence by doing E equals mc squared, so we get 2.78 times 10 to the minus 11 joules. Now, in the two reactions, fission is a chain reaction which is self-sustaining once initiated, while fusion requires high temperatures, high amounts of energy, high density, and to continue this particular process throughout. Now, the fuel of fission is uranium, which will need to be enriched, so we'll have to have more of the uranium-235 placed into it. Fusion needs just fuel from water itself, it is hydrogen. The waste of fission is it produces radioactive waste, which is a long half-life, high levels. Radioactive waste needs a long amount of storage, but fusion produces effectively no radioactive waste. It will actually just produce helium as its product. Now, in terms of safety, in fission there's always the possibility of a serious accident or leakage of radioactive material or a nuclear meltdown, whilst in fusion it's very unlikely to produce a serious accident and there's going to be no leakage of radioactive material. So that brings an end to our revision session today. So hopefully, if we've been successful and we've learned in today's revision session, we can answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So I hope you've enjoyed this session where we've looked at practice questions for AQA A-level physics paper 2. Thank you very much and have a lovely day.